So in today's lecture, we will discuss about continuous functions. Generally speaking, this is not a type of function, but it is a property of function. So a function is said to be continuous when its graph is a single unbroken curve. For instance, let's consider 2 points on the x-axis. Let's say point A and point B. This is also going to be the interval. So we'll suppose that a function starts from x equals to A. Function ends at x equals to b. Now, while sketching the graph, we have seen that we didn't lift the pen as we drew the graph from point A to point B. So this is an informal way of stating what continuous functions are, just to give you an idea. Now, how to differentiate between functions that are continuous and that are not continuous. So not continuous means it is discontinuous. For instance, let's consider the function f of x is equals to x squared minus 25 divided by x minus 5. Now, we see that this function does not exist at x equals to 5. That's because if we substitute the value of x with 5, then we'll have 5 squared, which is 25. So we have 25 minus 25 divided by 5 minus 5. So this gives us an indeterminate form 0 over 0. Indeterminate form means we cannot determine the value of this function at this particular point. However, if we use some algebraic techniques, so that means x squared minus 25, so this can be also factorized as x minus 5 times x plus 5 divided by x minus 5. Then the function f of x reduces to x plus 5. Now this is simply a linear function, and if we try to plot this function, then our function has a positive slope and has an intercept of positive 5. So this is a linear function, but actually this is not a complete picture, even though it looks like a smooth continuous curve, because while drawing from, let's say this is the point A and this is the point B. So as we go from A to B, it looks like this particular function is very smooth and continuous, but actually it has a discontinuity at the point x equals to 5. So let's say this is the point x equals to 5. So here we have a discontinuity, and to represent it, we have to put a hole here. So there is a hole in this point. So this particular function is continuous everywhere between the interval a and b, except at this point x equals to 5, where there is a hole. So hole means it has an indeterminate form of 0 over 0. So this is continuous everywhere and discontinuous at x equals to 5. So let me write it down. So our function f of x is continuous everywhere except at x equals to 5, where it will be discontinuous. Then we can have another type of discontinuity. Another type of discontinuity will be the jump discontinuity. So let's consider the function f of x given by absolute value of x divided by x. So this particular function has got two cases. So we'll consider case number 1 when our x is a positive number. So we are taking x greater than 0. So in that case, the absolute value of x, that becomes positive x, and in that case f of x will be x over x. So this is positive 1. So that means if we are to plot the graph of this particular function, so for x, so this is the origin, so we have to consider the positive x values. So here it has a value of plus 1. Then in case number 2, when our value of x is less than 0 or it is negative, and then the absolute value of x is simply negative. Then in that case, f of x will be equals to negative x divided by x, and this gives us negative 1. So this means our function has a value of negative 1 for values of x less than 0. However, but if we are to ask the question, what is the value of this function at the origin, then there will be an ambiguity, because it can be either plus 1 or negative 1. However, we need a single answer. It cannot be both. So that means there is a discontinuity here. So let's put a hole two holes here. Now why this is called a jump discontinuity? Because let's say we are coming from left to right. So the moment we reach the point 0, x equals to 0, so the value of the function jumps from -1 to +1. So that means there is a jump discontinuity here. Although the function is continuous for x less than 0 and x greater than 0, it is simply discontinuous at the point x equals to 0. The third type of discontinuity will be when the function has a vertical asymptote. For instance, let us consider the function given by 1 over x. Now, at x equals to 0, the function simply blows up. So this will be undefined. Now, if we try to sketch this particular graph, so for x greater than 0, the graph will be, so that means when it is closer to 0, it's going to have a very high value, because it goes almost up to infinity. And if we consider for x less than 0, the graph will be, so here it has a vertical asymptote represented by this blue line at x equals to 0. Alright, a vertical asymptote at x equals to 0. So this simply means that when we approach the value x equals to 0 from the left hand side, so this is going to have a very high value of -infinity, or you can say the function goes to -infinity. And when we approach the value x equals to 0 from the right hand side, so it's going to blow up to +infinity. So this is the meaning of a vertical asymptote. So simply the function f of x is undefined, or you can say discontinuous at, I'll write it down, f of x is discontinuous at x equals to 0. However, if we exclude this point x equals to 0, so we can say that our function f of x is continuous everywhere except at x equals to 0, where it is discontinuous. And when we mean everywhere, it simply means from -infinity to 0, union 0 to infinity. There's a small note that I'd like to make here. A given function is continuous within its domain. Only then it will be a continuous function. Now let's talk about the formal definition for continuity using limit. So our function f of x is said to be continuous when for every value of c belonging to the domain, f of c is going to be defined and the two-side limit f of x when x approaches c is equals to. So this is how we can define or check for the continuity of a function. So let's apply this particular definition with the help of few problems. So we'll discuss the continuity of each of the three functions. So let's begin with the logarithmic function. So if we try to sketch the graph of the logarithmic function, so you can always use Desmos. Now, first let's talk about the domain of this particular function. So the domain of a logarithmic function is given by 0 to infinity, because the function is not defined for x equals to 0, it's only defined for values of x greater than 0. So since our function has the domain on the interval 0 to infinity, so we'll say that f of x is continuous for x greater than 0. For all values of x greater than 0, the logarithmic function is going to be continuous, and for values of x less than 0, it's going to be discontinuous. Now coming to the second function, which is given by sin x over x, we have already discussed while we're considering limits. So this is how the graph of a sin x over x function looks like. So at x equals to 0, the function is undefined, so that means it has a hole. So here the domain will be all real values except the value 0. So the function g of x is continuous everywhere except at x equals to 0, where it is discontinuous. And coming to the third function, 1 over square root of x minus 2. So here we see that the function is not defined at x equals to 2. So that means we have a asymptote at x equals to 2 because the function simply blows up to infinity. And if we try to plot this graph, then this will have, so this is the graph of h of x. So what is the domain of this particular function? So the domain is negative infinity to 2. So 2 is not included, union to the infinity. The function h of x is continuous everywhere except at x equals to 2 where it is discontinuous. So we need to check the continuity of this function f of x given by 4x plus 5 divided by 9 minus 3x at x equals to 1 and x equals to negative 3. So let's begin with the first value of x. So we have x equals to 1. We first begin by evaluating the value of this particular function at x equals to 1. So this will be 4 times 1 plus 5 divided by 9 minus 3. So we have 9 divided by 6. So this is 3 over 2. So this is the value of the function at x equals to 1. Next, we try to find out the limit of this particular function, the rational function 4x plus 5 over 9 minus 3x when x approaches the value 1. So here also we'll see that this will be simply 4 times 1 plus 5 divided by 9 minus 3 times 1, which gives us 3 over 2. Since the limiting value of this function f of x when x approaches the value 1 is equals to the value of the function at x equals to 1, so we'll say that f of x is continuous at x equals to 1. Let's go to the second problem. So here we want to find out where we need to check the continuity of this particular function at x equals to, so this is not negative 3, this is positive 3. So let's try it out. So we have a function given by 4x plus 5 divided by 9 minus 3x. So at x equals to 3, f of 3 will be simply equals to, so we have 4 times 3 plus 5 divided by 9 minus 3 times 3. So we have 12 plus 5 divided by 9 minus 9. So we have a 0 in the denominator. So 17 divided by 0. That means the function is blowing up to infinity. Now, that means it's undefined at this particular point. So we'll have to check the limit of this value as x approaches 3. Now this is going to be a two-sided limit. That's because it's infinite value. Now we cannot say for sure if this is blowing up to positive infinity or to negative infinity. So that's why we need to check for the two-sided limit. So first we will check for 3 plus. So that means we are going to approach this rational function from the right hand side as we approach the point 3. So for this we will need to sketch the graph of this particular rational function. So let's use Desmos. So this is the graph of this particular rational function, and we have a vertical asymptote at x equals to 3. So clearly when we are approaching the value x equals to 3 from the right hand side, we see that this blows to negative infinity, and if we approach the function at x equals to 3 from the left hand side, then it blows to positive infinity, as is evident from this graph. So clearly the limit, so we can say the right hand limit is not equals to the left hand limit. So we can say our function f of x is continuous everywhere except at x equals to 3 where it is discontinuous. Also, one more thing, the domain of this particular function will be from negative infinity to 3, including 3 to infinity. So I can say that this function is going to be continuous everywhere in the domain except at x equals to 3, and hence we have not included 3. So we are using an open interval here.